So this talk is about certain object which we call definite connections. Connections, and this is based on this is joint work with Joel Fine. Joel Fine. Basically, it's a 2 years old paper, but it is always good to think about this problem and to try to, for example, simplify the proof that we have. And maybe I will try to just, at least a little bit understand better the proof and slightly simplify it. And this is what I kind of, will be the only tiny new thing in this talk. Basically, what I will do, I will first formulate the theorem, just the theorem that the result that will be proved. So theorem. And then I will say some words. So let M4, E3, and nabla be the following data. So the for manifold, and then E3 is a rank 3 bundle, rank 3 bundle with a metric, with Euclidean metric, and nabla. Finally, nabla is a metric connection. Okay. So we have this data, just 4-dimensional manifold, compact, rank 3 bundle, and a connection on it. And next, denote by f nabla the curvature of this connection. Of this connection. You can think like, well, here's the picture. You have a 4-dimensional manifold M4. Basically, you have a rank 3 bundle, and the connection gives you a parallel transport. And when you go along the little loop, you get a holonomy, and you then turn this to 0, and you get a curvature operator. And so we impose the following conditions. So suppose the following holds. Suppose moreover that basically we have the largest possible non-degeneracy of the curvature. F nabla of uv is always non-zero if u and v are not proportional, and v are not proportional. So this is the object that we are interested in. Then what is the theorem that I will kind of speak about today? The theorem is like this. So we want to understand this object, and we want kind of to impose one additional condition, a certain symmetry on it, like the simplest possible symmetry. So suppose that there exists an S1 action, S1 symmetry of this data. So basically, there is a certain circle acting on 4-dimensional manifold, and this leads to the action on the bundle, and this preserves connections. So then the corollary is M4 is either S4 or CP2 bar. So CP2 bar is CP2 with opposite orientation, and basically these objects somehow they have natural orientation. So this is the statement that kind of that I want to discuss. Very generic geometric object, certain geometric structure. It is not very well studied. Like not so many people studied it, but at some point it popped up in works of two persons some time ago, Reznikov and Weinstein. We're considering things which are a little bit similar. Okay.
Bar is with opposite orientation.
Sorry?
So bar is with opposite orientation.
Yes. Somehow, yeah.
But the conditions I don't find an orientation.
That's true. They know orientation and condition, but somehow, for some reason, this geometric structure gives you an orientation somehow. Like, I mean, it's just like there is a certain additional orientation inside of it. But you're right that it's kind of it's not present in this definition. Yeah, and so this is the theorem, and this is the theorem, and just the definition indeed is that definition is definite connection is this geometric data, is the above geometric data, above of geometric data, namely M for E3 nabla and F of nabla UV is non-zero. So this is the data. Okay. So this statement can be seen as some kind of sphere type result in differential geometry. But I want first to kind of I want to kind of point out to some classical result of Hitchin where same kind of manifolds appear, basically. So that to show that this is not the first time that such situation happens in mathematics, and in order to do this, I want to recall your just definition. What is a twistor space? Definition. Twistor space. Space is so like let M4 be, say, a Riemannian oriented manifold, and consider the bundle, the S2 bundle. So it's like this Z6 over M4 such that the fiber at each point of X are X inside of M are operators operators J such that J squared is equal to -1, J J preserves metric, and induces the proper orientation, the proper orientation on M. On M. Okay, so if you just solve this, I mean, I'm sure most of you have seen it, but if you solve such a problem of linear algebra, when you have a four-dimensional R4 with a metric, Euclidean metric, and you look for such operators, you get S2, basically the S2 worth of such operators. So in this way, we get a twisted bundle of our four-dimensional manifold, and so one reason why mathematicians were interested in this, as far as I understand, is that this bundle has a natural almost complex structure, which is integrable, if the metric on M4 is say anti-self dual. And in this particular case, so we get a certain complex manifold, complex three-dimensional manifold from a four-dimensional manifold. And basically, the question, the relation to this to our statement is that in I think 1971, approximately, Hitchin asked when these twistor spaces are Taylor. Basically, it's a very natural question. Like you came up with a certain construction of complex manifolds. You want to know when are they Taylor, or like when are they come from algebraic geometry. And as far as I understand, he was surprised a little bit to prove the following theorem. The twistor space, the twistor space is scalar if and only if M is equal to S4 with round metric, or M is equal to CP2 bar with Fubini study metric. So in this particular case already it makes sense to put orientation here, because twistor space, in the definition of twistor space, we use orientation on a manifold because we consider J's that preserve orientation. So this was his kind of statement, and what we are doing is we are kind of trying we are going in a somehow a bit similar direction. The difference is that we start with something of a much more general nature. It's basically it's not a metric, and we don't impose like anti-self-dual metric is a certain equality, while definite connection is an inequality. Okay. So now basically I will start to kind of to describe a little bit the underlying geometry. So so when you have this like data M4, E3, and nabla, what you can do, like it's immediate thing, you can get an S2 bundle from this data. So what we do, we consider the S2 subbundle of E3 like consisting of unit vectors and this thing will kind of this gives us an S2 bundle. So we have like Z to M4 S2, and we will see in reality that this bundle really plays the role of for us like it will kind of play the role of a twistor bundle, which happens in this Hitchens theorem. So now, sorry, maybe I was a bit quick. Maybe I should give you like one more connection to something standard. It's just that again, definite connection something very, I would say, unusual. It's kind of its animal is not very common. So what does it kind of, what does such an object might remind us? Definite connection. It might remind us, for example, like a notion of kind of sectional curvature. So remaining manifolds, Riemannian and fourfolds. So we can consider Riemannian fourfolds, and we can think about sectional curvature, yeah? Curvature. So what is sectional curvature is like it's very similar idea. You take two vectors here, like on your manifold, and you calculate the Gaussian curvature at this like two plane, and then you can ask, what happens if this curvature is always non-zero? Yeah. What can we say about the manifold? Suppose this curvature is almost always non-zero, and then basically what happens is that we have two possibilities. Either we have positive sectional curvature, yeah, sectional curvature, or negative sectional curvature, yeah, sectional curvature. So it is more than zero and it's less than zero, yep. And note that only manifolds with positive sectional curvature can admit an S1 action. only manifolds of positive-sectional curvature admit an S1 action. And in this case, there is a theorem that is analog of our statement. Namely, if we have a positively curved manifold, four-dimensional manifold with an S1 action, then it is either, well, basically it is S4, RP, well, say oriented, then it will be S4, CP2, or CP2 bar. So this is basically, this is the whole list of manifolds that have an S1 action and positive sectional curvature. So this is why kind of our result is analog of this statement. But again, so this is how far, or is it CP2 blown up in one point as well? Or I forgot. Yeah. So this is how far differential geometry can go. Like differential geometry can say that take positive curved manifold as one action, then this is the classification, and this is work, say, of Kleiner. On the other hand, problem of say classifying all metrics of positive sectional curvature on a four-dimensional manifold is just like completely open. No one knows how to proceed. So, and this justifies for us also the introduction of this S1 symmetry. So it's not little to, I mean, it's not too much to ask for such a symmetry. Okay. So in order to say something about this result, we need to connect this geometric structure to something more familiar to in geometry and in mathematics, and namely we kind of there is a direct relation between different connections and symplectic geometry. So, claim. So there is a direct link between different connections and symplectic geometry. Okay. And namely, so here's a lemma. There is a so you see, like, where in this setting we have this four-dimensional manifold, a rank 3 bundle, and connection. So, and then we get this two-dimensional S2 bundle, yeah. And the lemma is like this: there is a natural to form closed to form on Z, and it is close to form, say, omega, and it is non-degenerate if and only if nabla is definite. Okay, so what I will now explain, I will explain the following: is that imagine that you have like such a data. We just have M4 bundle connection. Then on Z we immediately get a closed to form, and this closed to form is symplectic if and only if the connection is definite. So this is kind of one-to-one correspondence between symplectic somehow certain symplectic structures and these connections. And I want a kind of this lemma. I will not prove it, but I want to draw a picture which kind of explains why we have this symplectic form. So the picture is like this. So we have our four-dimensional manifold M4, yeah, and we have this rank 3 bundle, yeah, and we have a connection. Okay, basically we have a connection somehow, and we have like two spheres here, yeah. And what we want to do, we want to construct a closed to form on this bundle. So how to do it? So the claim is that there is a natural connection on the vertical bundle of this vibration. Okay, so this is the claim. You have this bundle, and you have S to bundle, and we have like here a rank to bundle, yeah. Rank to bundle, which is just vertical. And the claim is that there is a natural connection on this bundle. So there is a natural parallel transport on this bundle. So how to see it? It is not very hard to see. So you see, like, first of all, if we restrict ourselves to each fiber, yeah, then clearly, like, each fiber is a unit sphere, and there is a like Levy-Chevit connection on the two spheres. So we have a connection in the in the vertical direction. This is obvious. So why do we have the connection in all directions? And here the idea here is the following: is that basically you see, whenever you have certain path downstairs on the base, from this nabla we get a parallel transport of our two-dimensional sphere somehow. And so basically this sphere moves, and together with it all its point moves, and also like the vertical fiber also moving. So this is why like we get connection on the vertical vibration. And whenever you have a connection on a rank to bundle, from this you get a two form. So there is a connection on the vertical bundle of this vibration. So its curvature is a two form. And it turns out that this two form is closed if is symplectic if and only if the connection is definite. Okay. So now I want to give you one more kind of one more statement which you see, as I told you, there is a parallel between this geometric object and Riemannian geometry, positive and sectional positive and negative sectional curvature. And now I will kind of state to you kind of this parallel in terms of like of a certain proposition. Just what is a positive different connection, what is a negative different connection. So this will be a proposition proposition. I will first state it, and then I will explain to you one notation in this proposition. So suppose connection double is definite, then we basically have two possibilities, that either Z is diffeomorphic. Then we have two statements. First, that Z is diffeomorphic to the twistor vibration of M. So this first statement, vibration of M. This is first thing, and then here we have two possibilities. Either first term class of Z is equal. I mean, it's in cohomology. Its class is equal to two classes of omega. So basically, this is inside of second cohomology of our Z, or C1 of Z is equal to 0 inside of H2 of Z. Okay, so we have two possibilities basically. So this is so this kind of restricts a lot our vibration. So already we see that if we take arbitrary rank 3 bundle over M4, it will probably never be it will never have a definite connection, just because associated sphere bundle will not be twistor vibration. So the associated twistor bundle must be twistor vibration, and then we have here two possibilities. Okay, and this possibility is called so in this case we call our connection positive definite. And this is like negative definite. And basically I should give you examples like of such things, like really that such examples exist. So examples for this is that if you take for example sphere S4 with round metric, with round metric, then the twistor space, corresponding twistor space Z, is just CP3. And well, this condition is satisfied. So this is a kind of Fano manifold. Manifold. And this an example for such a manifold, we should take hyperbolic four-dimensional space, and we should take its twistor vibration. We should take here. I forgot to say the bundle that we take here is lambda plus. And here again lambda plus. So rank 3 bundle of say self-dual forms. Okay, so in this case we get CP3, and in this case we get certain non-compact space. It's non-compact, but then we can quotient by say by discrete isometries of H4, and then for each hyperbolic for manifold we get we associate a certain symplectic Calabi-Yau 6-dimensional manifold.
What's the map from CP3 to S4?
It's a very nice map. So just it's like it's a generalization of Hopf vibration. I will. It's really cool in the sense. In order, so there are different ways to see this map, but one possibility is like this. We, and please, if I'm wrong, please correct me. But I think it's like so. One possibility is like this: we take C4, and C4, of course, is associated to CP3. Yeah. And now C4 we see it as C2 plus C2. Yeah. And now we act on this thing by diagonally by SU2. Yeah. So like this, and basically we act diagonally by SU2, and now again in this C4 we should consider S7 7-dimensional unit sphere, and then basically you will get a vibration over S4 with fiber with fiber S3 or CP1. So this kind of you have a real family of lines.
Yeah.
Like it's a two-parameter family, complex two-parameter family of lines, or a real four-dimensional parameter family of lines. Also, what is kind of nice about this non-compact manifold is that it can be seen as a total space of bundle of -1 plus of -1 over CP1. So this is a kind of quite well-known bundle over CP1 of -1 plus of -1, and it turns out that symplectically this is exactly this twistor space. Okay. So, and finally, let me formulate the conjecture that we kind of think about, and which is a generalization of this result. The conjecture is the following: is that
do you mean O minus 1 or
O of -1 plus O of -1.
symplectically.
No, basically it's a rank 2 bundle.
Yeah, okay.
Okay, so conjecture is basically suppose M4 E3 nabla is a positive definite connection. Then M4 is diffeomorphic to either S4 or CP2 bar. And this is kind of analog of Hopf conjecture somehow. Well, in some sense, Hopf conjecture tells that S2 times S2 doesn't have a positive sectional curvature. And we kind of say that this kind of there are only 2 examples of such guys. And what we can prove is that provided we have a S1 symmetry, this is indeed true. And this is good because usually when people construct, often lately there were a lot of construction of metrics, and often the simplest possible case is like to construct something with a symmetry. And this is the simplest possible symmetry that you can imagine. So somehow, like if there is something which is like violates this conjecture, it is highly asymmetric. Okay. now I should say a little bit something about okay, maybe I should also say kind of one word about why one can believe in this conjecture, or not believe, but say at least what can this remind a little bit? Say is it just a remark? So in algebraic geometry, if we have such a relation that if Z is say a complex projective manifold, then this condition C1 of Z is equal to lambda times omega with lambda more than 0. This means that Z is a Fano variety. And like in each dimension there is only finite number of Fano varieties, at least in algebraic geometry. And how this kind of points to certain restrictions on such objects. Okay, so now I will tell maybe one word about the proof. So basically, since we start with any manifold, we have a lot of things to prove because like four-dimensional manifolds, it's impossible to classify them. Like there are a lot of them, and in particular, the first invariant, which is how is the most kind of nasty, is that we have pi1 of M4. So these manifolds, in principle, can have arbitrary fundamental group. And so the first step in proving such a statement like this is to prove that first is prove that pi1 of M is equal to 0, so that our manifold is simply connected. Okay, and here so how one can do this in this particular case? So we need to use theory of Hamiltonian S1 action. So use theory of, kind of, it's an activity of Hamiltonian S1 actions. S1 actions. So the first observation is that the action of S1 on Z is Hamiltonian. So this is the first statement, and then there is a very nice, quite simple result about fundamental groups of manifolds with Hamiltonian S1 actions. So this is a result by certain lady. I will state now this result. the theorem is like this. Theorem. Suppose, let me, maybe I will write it down. So let Z omega be a connected compact symplectic manifold equipped with a Hamiltonian S1 action. Then their homomorphism pi 1 of Z mean to pi 1 of Z is an isomorphism. I will tell you now what this means, isomorphism. Isomorphism. So basically, whenever we have a Hamiltonian S1 action, this Hamiltonian attains minima somewhere. Like some minima somewhere. So basically, we have a Hamiltonian S1 action. For example, I don't know. Let's say S2. Yeah, we have this Hamiltonian S1 action, and the statement states that if we take all the points where the Hamiltonian attains its minimum, that means that fundamental group of this is equal to the fundamental group of the whole space. And what is nice in our particular case, in the case that we study, in this case we have this observation is that minimum of Hamiltonian is obtained on a surface in our manifold in Z, on a surface or a point in Z. So in particular, the fundamental group of Z can be at worst pi 1 of some surface of some genus. And I wanted, but I guess I don't have time. I wanted to give a very kind of certain new way to prove it. But I think I already used 15 minutes. So I don't know. Maybe let me. I will just formulate a lemma. Just let me formulate a lemma, and then I will prove it. Just kind of to give a taste of this. So just it's a lemma. It's an elementary lemma of symplectic geometry, or say simple algebraic geometry. So lemma let CG be a surface of genus G, L1, L2 be two line bundles, suppose we have a Hamiltonian S1 action on the total space on the bundle L1 plus L2. Some of n bundles, and we have like very simple action with weight 1. Then somehow whenever you have this curve and like rank to bundle Hamiltonian here, for example, is equal to 0, and here it is function is positive. And what we can do, we have symplectic manifold. We can calculate the volume of the reduced space. So basically, then at level t. So then the statement is that the volume of reduced space at level t, volume of reduced space at t is equal to t times 2 omega g minus t times d1 plus d2, where d1 and d2 are degrees of L1 and L2. Degrees of L1 and L2. So basically, you can calculate the volume of reduced space by a very simple formula. And and the point is that of this volume, it must be positive, because if you start with a symplectic manifold and you reduce it, I mean, it cannot be negative. And this kind of explains that minima of Hamiltonian cannot be achieved on curves of genus more than 0. So that's it.
Questions for Dmitri or comments? Here, the two line bundles, they're supposed to be the normal directions to this Z min.
Okay. Somehow, like you have your curve and you have like normal bundle, and linearly, locally, it's like it's the neighborhood of a sum of two line bundles. And somehow you can ask how thick can be this neighborhood, and turns out it's quite small. So this is kind of the idea. So this is just kind of it's a very simple question. Suppose you have a symplectic structure, say not on the whole line bundle, but on a part of it. So how large part how thick can it be? And this formula tells you somehow that if this degree are positive, then it cannot be too thick, because this volume becomes equal negative, which is kind of impossible.
Here, when you say weight 1, you mean rotating the line bundles at speed d to their degree, or just speed 1?
Speed 1.
Speed 1. Okay.
Yeah.
Maybe this is a elementary question, but
Yeah.
you proved that by 1 is 0, but how do you prove the rest of the statement?
Okay, so there are two things to prove, and really somehow our proof is really very similar in some sense to this differential geometry, with only the difference is that there is no differential geometry, so there is no method. So basically, next thing to prove is that the plus of this manifold is equal to 0. And in the differential geometry, this is done by Bochner formula somehow. For us, this is a straightforward way to do this, and somehow the favorite way to do this is to use analog of certain. So in algebraic geometry, there is something which is called Hodge index theorem. Hodge index 7. Basically, this is a statement about like signature of certain signatures of certain succession forms in algebraic varieties. And so we should think about this manifold Z as an analog of symplectic manifold, which is somehow rational, birational to CP3. And this gives us b plus equal to 0. And when b plus equal to 0, the number of manifolds is immediately very, very small. It is like connected sums of CP2 bars. And then you can take at most, and now if you are here, then the number of connected components can be at most 3, because now we can calculate the volume of the symplectic manifold, and it should be positive. So it's at most 3, and now you have two cases that you have to prove that they don't exist. Probably this should work also for orbifolds. So like that all the orbifolds which are possible, they are already known. So this is
What happens with a definite connection for an orbifold?
just that they all come from anti-cell to Einstein matrix, something like this. I mean, if you have S1 symmetry, this is kind of so the analog of Hitchin statement should be true, probably.
This surface, so this surface you have in Z, right?
Yes.
So how does it relate to M? Is it
Very good.
diffeomorphic to something in M?
Exactly. Yeah. So basically, so if you have like M4, yeah. Basically, then if you have an S1 action, and it will have fixed points. They will be just points, isolated points plus surfaces. And over each point upstairs we will have 2 fixed points in the twistor space, and over each surface we will have 2 copies of a surface. And somehow what happens is that when we lift it upstairs, it turns out that Hamiltonian must have maximum or minimum on each of the surfaces. This immediately tells you that there is only at most one surface, and this is this genus like given by this.
Kind of pitch to have in your head could be to let S1 act on the 4 sphere, keeping fixing points and rotating around a 2 sphere, and imagine the lift of that on CP3. You have 2 rational curves that were fixed, and then 1 twistor line over a fixed point, 2 fixed points. Well, actually, you'd have the whole line fixed then.
This is if you describe CP2. If you take S4, it's just you describe CP2.
Yeah, you're right.
Yes. So just in CP2 you have you can fix one point and you rotate everything around this point, and you have fixed line, and then in a flag variety indeed you have 3 fixed lines.
So you can have twistor lines over these isolated.
Yes. Yeah.
There are no more questions. Let's thank Dima again.